Okay, then so let's start the second day of the second day. The first speaker is Sung-Soo Kim. He's going to tell us about 5D non-Lagrangian series index function O7-planes.
Thank you very much.
Oh.
Okay. Thank you very much for the introduction and also the illustration. So today I'll talk about the long title topics with the long title. The three things are main focus: non-Lagrangian theory, index function, which includes the superconformal index as well as partition function, and O7-planes. This work is based on this work is based on the three collaborations: Kim and Sung-Soo Kim and Fries. This will be the main focus today. And another one is Hirotaka Hayashi and Kim Young-Min, Toshiaki here. Another one is Xiaoyin and Satoshi and Toshiaki. Okay, yesterday we talked about 2D, 3D, 4D supersymmetric gauge series. I think it's time to talk about other dimensions. Today, at least, we will have a morning session. It's 5D superconformal theories, and hopefully, maybe somebody will get to the 60s this week. Okay. So let me first motivate that there has been a lot of progress on the 5D superconformal theories. So since the Cybox Center work on 5-dimensional SU2 gauge theory with some number of flavor, it was like 1996. He showed that there are non-trivial superconformal theories in UV. So the number of flavor is from 0 to 7. And usually this theory is referred to as a EN theory. The N is, you can think of it as a rank of a flavor symmetry. So EN, probably you're also familiar with the E8, E7, E6. Those are the EN means. And that also means that the flavor symmetry will be exceptionally symmetry like E8, E7, E6. But you can also formally extend to lower EN, like E5, which is D5, E4, A4, something like that, all the way to E1, SU2, or E0, even E0. So it's E0 means that there's no symmetry at all. And since then, this study of superconformal theory in 5 dimensions has expanded a lot. Usually, and they are computing this physical observable. One of the important one is known as the Nekrasov instanton partition function. It is partition function for R4 plus S1 on the omega deformations, omega background. Notably, there are three main computational tools for this partition function. These are one of them is ADHM construction based on the instanton quantum mechanics. Another one is topological vortex based on the it's like a Feynman diagram based on the type 2B brain webs. Another one is mathematical relations coming from the blow-up expression. I think this audience, there are many experts here. And then another observable is a superconformal index, which is a twisted partition function on the, let's say, S4 times S1. In particular, yesterday we talked about the superconformal index appearing here. I will also mention the superconformal, the index later in more details. Another observable is a Cybox curve, and also magnetic quivers, which captures the Higgs branches, is also connected to the three-dimensional Higgs branches together with the mirror symmetry. Let's see what else. Okay, there's been many people working on this. Maybe I missed some of them, but you know, it also tells you how many people are interested in it and wants to make a progress. On top of that, there will be also defects, and then another interest is also classification of the superconformal theory in 5 dimension. Probably the expert here is Dan Xie. And on top of that, along the type 2B 5-brain web, there has been also some progress. The one that I want to mention here is usually when we talk about the type 2B, this brain configuration, then we have a SUN gauge theory or SP, SO gauge series. But quite recently, we can extend it to this, even to the exceptional gauge theory G2. So that's quite amazing things, because usually people thought the exceptional gauge theory is very difficult to construct based on the this type 2B brain configuration. And also from the matter point of view, not only the fundamental hypermultiplet or antisymmetric or symmetric, there also has been rank 3 antisymmetric hypermultiplet was also constructed. This is a notable progress. But yet, there are still some issues requiring that we have a better understanding for this, which is the first thing is a superconformal index for non-Lagrangian theory. Maybe you heard of superconformal theories with the gauge series, and you check the dualities and other symmetry enhancement at all. But maybe you haven't heard about the superconformal theories. Superconformal index for the non-Lagrangian series, which is difficult and is challenging. Another one is a 5-brain web. The construction of exceptional gauge series beyond this G2 gauge theory. Let's say gauge theory F4, E6, E7, and E8 is far more difficult. Another thing is that the introducing oriented forward. There's an O7 oriented forward, O7 minus and O7 plus depending on charges. But relatively, O7 minus can be understood in a well, in the sense that Ashok Sen taught us that it can be split into 2 7-branes, and whenever you see O7 minus, you can think of it as you split into 2 7-branes, and that's the one way to understand it. But on the other hand, O7 plus cannot be split, and it's still difficult to even compute partition functions or do something with this. It's still remain challenges. So in this talk, I will talk about these 2 challenges, and I will propose a simple ideas of dealing with these 2, and based on the type 2B 5-brain web. So here the type 2B 5-brain web is crucial to better understand these 2. Okay. So far, any questions? Okay, so let move on. As I said, this 5-brain web is important. So let me talk about the 5-brain web a little bit, and also make a connection to the non-Lagrangian series. And this work is based on these 3 collaborations. So the type 2B brain construction is that the gauge series can be embedded into brain configuration known as a PQ 5-brain web, or in short, 5-brain web. Usually you've probably seen this diagram. Here we have the brain web introducing NS5 brains and D5 brains. They are referred to as brain charges 1, 0, D5 brain, and NS5 brain called 0, 1. and there are like a bound state 1, 1 or 1, or in general you say PQ. So therefore, their configuration is collectively called PQ fibrinoid. So they are the same dimensional branes. So and then they have some common directions that actually covers the Wall volume of the 5-dimensional theory. Let's say from 0 to 1, 2, 3, 4. But they have a not common direction is drawn here. Let's say this horizontal line is the direction where d fibrane is extended, and the vertical line is ns fibrane is extended, and they make the some configuration like the charge conserving configuration like this, and then after that they become the 1, 1, which is a bound state of these two, and this one captures the SU2 gauge theory. A way to understand is that there are d fibranes is suspended between two ns fibrane. So here you can think of this. There's a fundamental string connecting d fibrane to another d fibrane, which plays a role of the W versions of the SU2, and there's another string connecting these two ns fibrane, which is D1 string. D1 string is responsible for this instantons of this theory. So due to the fact that the homotopy group of this SU2 is a G2, it allows you to two different configuration, often refers to the discrete theta angle denoted by either 0 or pi. And then, so SU2 theory in 5 dimensions therefore have two different configuration. One is denoted by this like a symmetric rectangular, and the other one is a symmetric rectangular. And as you can see that this is a symmetric configuration. There is some difference in the global symmetries. The symmetry indicates that there may be some symmetry. In fact, there is the symmetry coming from the instantons. It is SU2 symmetry. I will correct this SU2, but not to be confused with the gauge symmetry. I'm talking about the flavor symmetry. The flavor symmetry for SU2 actually has U1. So there, the global structures are different. On top of that, in fact, this BPS string configuration also different, but they have the perturbatively the same. So in other words, their instanton configuration or BPS state associated with the instanton partition functions are actually different. Anyway, these two, the brain, BPS in this type 2B brain configuration actually captures the Coulomb branch configuration. And so basically this is somehow, it is under some expectation value of the scalars in this theory, SU2. And the shrinking limit gives rise to the superconfirmation theory where there's no scales. Okay. So let me also introduce not just rank 1 theory, but rank higher than 1. Here rank, I mean the gauge group rank. So these are some examples of SU3 rank 2 theory. From the SU3, we can introduce transaminal level. Let me denote by this kappa. Here we have SU3 with the transaminal level 0, and this is transaminal level 3, and this is transaminal level 6. So but they have this like two compact phases that give rise to number of compact phases correspond to the rank of gauge groups. Here we have 2 of them. The other also have 2 of them. And also you see that there are 3 parallel lines of 3 D5 branes. Then fundamental string connecting them basically give rise to the fundamental the W versions for the SU3. But actually they have different shapes, right? So different shape is captured of this transaminal level. One of the things, probably if you are not familiar with this transaminal level, how they are connected, one way to to see is that if you have this web and you make like a 180-degree rotation, or you split the web, and it will be upside down figure, then Chern-Simon level, I don't know what happened. Chern-Simon level is flipped. So for example, if I have this upside down figure where there are two lines widely open and there's no two lines parallel toward the down direction, and then this will be minus 3 Chern-Simon level. Okay, so if you look at if you have this one in mind, then if you look at the first one, you like take a 100-degree rotation and you will get exactly the same one. That means that whatever the Chern-Simon level is, it is a minus itself. Therefore, it will be Chern-Simon level 0. And another thing is that here SU3 with 3, or in general SUN with n, will have always some symmetry was coming from the like SU2 symmetry, and this symmetry is also captured in the brain web as a parallel lines. So if you have SU3 with 3, then you will have there's two parallel lines that captures SU2 or SU3, and therefore it will be SU3. And then as you change the Chern-Simon level, their like the angle will get narrow and narrow, and this diagram is obtained after doing some Hanna-Newton transition. Hanna-Newton transition is the transition of the brain, where the brain across another brain, there's a creation and annihilation of the brain, and there you see that there are two parallel lines. Is actually is created line due to the Hanna-Newton, and this therefore it explains the higher Chern-Simon level. So particularly I introduced this because this one has some common feature, which is there are two parallel lines and there's also two parallel lines. And this also indicates that the global symmetry of these theories have the SU2. So So let me summarize this from the brain web. Here I didn't mention, but the 7 brains can be attached to the end of this 5 brain, and they're denoted by this dot or point, and then they are actually extended the transverse direction of a 5 brain web, like this direction that, let's say, coming out of this plane. The parallel lines indicate that there are some flavor symmetries. For example, there's no parallel lines, therefore this will be the U1. And this one has parallel lines, although they have the same parallel lines, but this one is SO3, but this is SU2. I'll talk about this one later. But also, this will be very crucial point that brain also teaches that how the theory can be Higgs, or how it has Higgs branches. I will also talk about this one later.
Just to make sure, so this flavor symmetry is enhancement of internal symmetry at the SFT points, right?
Yeah, it is enhanced flavor symmetry. Yeah, that's really right. So like in the Coulomb phase is U1, but the UV will be enhanced. Okay, so also all the flavors or hypermultiplets. So also described in the brain maps. So fundamental hypermultiplet, sometimes I call it flavors, described by this just introducing B7 brain, which are these dots. So in this case, as an example of some particular SU3 with a Chern-Simon level, and we have 8 flavors on the left, on the right, together we have 8 flavors. Also, antisymmetric hypermultiplet is also described by introducing O7 minus, with half of them is stuck on the middle of this O7 minus. For example, this theory has 1 and 2 and 3 compact faces, so it's a rank 3 theory. For example, it will be like SU4 with some particular Chern-Simon level with 1 antisymmetric hypermultiplet. Okay? And symmetric hypermultiplet also can be described in a similar way, but the oriented force should be changed to O7 plus. So this example, again, let me count the compact faces. We have 1, 2, and 3, because the oriented force projection connects from the left to the right. 1, 2, 3, 4, 5. So we will have some SU6 theory with a symmetry map. Okay? So these are basic ingredients of the type 2B brain configuration describing SU theory with some particular hypermultiplet, fundamental, antisymmetric, and symmetric. Okay, so let me move on, and then now I'll talk about the non-Lagrangian theories. So non-Lagrangian theories along this Coulomb-Brunch algebraic law, it arises at the bottom of the algebraic law. For example, SU2 theory with a this discrete set of pi. I showed you this one before. There's a U1 symmetry that is not enhanced at the UV fixed point, but there are still these instanton particles in 5 dimensions. Instantons are in 5 dimensions of particles, so it can be considered as hypermultiplet. So usually I refer to the instanton hypermultiplet. So in the large mass deformation, we can decouple this instanton hypermultiplet, or in the geometric language, it's like this theory can be obtained from the M theory confected by Calabial, where the Calabial has method with the surface. In this case, it's Del Petro 1 or the F1 Hertzsprung surfaces, and it allows the flux transitions like this, and this is correspond to the changes of the masses, and we can take this to infinity, and then after this decoupling of the instantaneous hypermultiplet, you're left with this configuration, and geometry is known as the local P2 surface, or this one has no global symmetry, we call easier theory. So these are the theory that I refer to the non-Lagrangian theory with the rank 1, because this one has no W versions. So whenever we have the gauge theory, we have W version, which is described by a fundamental string connecting two different d5 ring. But here we have only one d5 ring, does not have a gauge theory description. And this is what I refer to as non-Lagrangian theory. And this one particular is a rank 1. But yet, there's another rank 1 theory which is it's not known, it's not well known until 1916, 2006-19. Laksha look at this theory where the SU2 theory is a particular tensor level either 0 or pi with a symmetry matter, which is SU2 case is the odd joint. And this one therefore describes the SU2 series odd joint matter, which is 60 theory or KK series. In particular, depending on the theta angle, theta equals 0, it describes the M theory, 6-dimensional M theory, M strings on a circle. And theta equals pi case is the A2 theory with a Z2 automorphism to it. And these two are the theories. But now we just talked about the SU2 with a discrete theta pi. One can decouple instantaneous hypermultiplet, and Laksha applied this exactly the same thing. Here, if we have a symmetric matter, so that is described by the O7 plus. So this part is SU2 with the theta pi, and now attached to the O7 plus, and describing SU2 pi with a symmetric matter, or other joint SU2 case. And then you do a similar decoupling. We do the instant hypermultiplet decoupling, and you left with the theory which is called local P2 with a one-odd joint. It can be understood as you have SU2 pi with a one-odd joint, but decouple one of the flavor. and then it actually has flavor symmetry coming from this symmetry. Okay? So it does have the flavor symmetry. Then we invent the name, which is E1, rank of the global symmetry is 1, and it's a different theory, it's a E1 pack theory. Okay? So there are two rank 1 non-Lagrangian theories. One is a local P2 or local P2 with the 1 adjoint. So now let me talk about the physical observables associated with the non-Lagrangian series. So non-Lagrangian series usually do not have the weakly coupled description, like the gauge series description. So it's difficult to, it's not so straightforward to compute the BPS observables. But there are some other progresses. Luckily, this local P2, this E0 theory, cycle-weekend is relatively easy to compute. Also, BPS partition function also computed by the many people. And, but their BPS partition function have the different structure. Usually, when you talk about instant partition function, that means that we have a partition function as an expansion of the instant fugacity Q. So instant part of the partition function has like a 0 instant, 1 instanton, and all the way to the infinite instanton, although we may not be able to compute all of them. So the BPS partition from the non-Lagrangian theory is because there's no instanton, instant is decoupled. So it is an expansion instead of the Coulomb branch parameters. So it's a different like a structure of the BPS partition function. Okay. Now let's talk about the superconfirmation index, which is another observables. Let me try to convey the idea why this partition function is possible for this non-Lagrangian theory, but superconfirmation theory, superconfirmation index is not easy. So first of all, let me remind you the superconfirmation index is it counts local BPS of operators in superconfirmation theories. It is robust, observable, as protected by any continuous deformation. So it's very useful to studying this non-perturbative phenomena. Like yesterday, we could check the dualities and also a symmetry enhancement. For example, as you ask whether these SU2 zeta 0 has is enhanced. Yeah, it is enhanced. You can actually compute the superconfirmation index, and you see that SU2 symmetry naturally arises. Also, in other dimensions, you can even check the supersymmetry enhancement as well. And also can be applied in the various dimensions, not only 5 but also other dimensions. Okay, so it's a good observable that checks the non-perturbative phenomena. So when you usually compute the superconfirmation index, we use the idea that it is robust. Therefore, we start with some weakly coupled description and compute this index from the instant partition function based on this localization. This is usually structure. It's a twist partition function, and with the fugacity is coming from the global symmetry of SO5, SU2R symmetries. These x and y's are the fugacity, the parameterizing this the global structure, and also how the masses and also hypermultiplet fugacies is introduced. And it is also a gauge invariant quantity, therefore we integrate their holonomies. Basic Coulomb branch integration is performed in this way. So the basic usually structure is that we have some Haar measures and a perturbative part and instanton part, and we put them together and integrate out this gauge holonomies, and what happens then after that we get the index. So now it is because we have gauge holonomies to be integrated out, but the partition function for this non-Lagrangian theory is expansion in terms of this gauge holonomies, unless you know all of them, all of order. So integrating them is very challenging. So therefore, because of that, this computing superconfirmation index for non-Lagrangian theory is I think in this way is, I think it's not easy or not, it's very challenging. Huh?
Sorry, let's just make sure. So super combined is the partition function on S1 cross S4.
Yeah, S1 plus S4, yes. So
Don't you have some like a contribution from North Pole and South Pole?
that's right. The insert part has to have, so that when we use localization, as the contribution from the fixed point North Pole and South Pole of S4. Yes.
Okay.
Okay, so I hope that I convey some idea that why the superconformal index for non-Lagrangian theory is very challenging. Any questions? Okay, so then we have some hint coming from the brains, which is, let me try to tell you about, although it's very challenging, there might be some other way to compute the superconformal index that hints comes from the 5-brain model. So here, here is a local P2, the non-Lagrangian theory. And then if I do some kind of Hana-Newton transition as well as SL to Z, for example, if I take this brain here, bring it to all the way to here, and then do some Hana-Newton. After Hana-Newton, I do the SL to Z. Now I'll have some configuration looks like this. Okay. So and then I also look at the SU3 with the transformal level 3, which has two parallel lines. And this one looks very much like this in a particular limit. In fact, there is some Higgs branchology flow that's coming from the SU3 transformal level 3 with the E0. There exists such thing. By the way, I think Ina mentioned that from the brain, this is easy to maybe it's not very difficult to see. But from like magnetic cables and others, it's not obvious to see this Higgs branches. Okay. So having this, let me explain how the Higgsing works. So what happens is that this parallel two line, their distance, is basically captures the instantons. Okay, there's a cube. So I intentionally put a different length of this brain and I'll put them in the 7 brain. Now I'm going to take the limit where the instanton factor shrinks, and they are getting together, and there will be like this. There are two lines here. There's one line. Up to this point is just a shrinking limit of this instanton, and this is still SU3 with the transformal 3. Here is a string so that we don't see much, but once the Higgsing arises, then the line, actually this line is also still connected, the other, this M spline is connected. Once the Higgsing is taking place, and this brain is reorganized such that there is the brain, like an S fiber is connected by these two 7 brains, and these two lines are only connected by this, the middle 7 brains. After that, they are completely now out of this system. Then we can take this the segment of the brain, NS5 brain, along the transverse direction of this peak plane. I refer to it X7 and 8, 9 directions, and then this part is now Higgsed away. Then as a result, rank shrinks, as well as the Coulomb rank shrinks, as well as also the flavor symmetry is also broken.
Sure. I'd like to understand what happened to the 3 parallel lines, which become just one, when you send Q to.
Right. This is so what has happened is that when we do this kind of Higgsing, so when this Higgsing happens, the 2 parallel lines, maybe I will use this. So probably there's some other like example that might be easier. Let's say I mean, this case is particularly difficult to visualize, so let me use some other example. So this is still SU3 theory with one of the flavors attached. Okay, so when Higgsing arises, so these two NS fibrates collide, and then so far I have not done Higgsing yet. It's like this, but they are on top of each other. Okay, so when this is it's a shrinking limit of this. When Higgsing is actually arises here, so we have to think about this configuration, which is still breaks. It does not break the supersymmetry, and there's something sometimes called S rule, which means that this line, the five branes not attached to one of the seven branes. So what will happen is that, so this line will be connected to this. Not the line was here, but it's connected to the other lines. So it will jump. So this line is now not connected to this fibrane, but jumps and to connect to the other line. So the rank was like here we have two compact bases, here one and another one, right? But now after this jumping, there is no closed bases here. So only rank is this phase is here. So it's a rank 1 theory. This is we start from the rank 2 theory. So it is like a SU3 with one flavor becomes SU2 with some particular theta angle. It happens that it's SU2 with 3 pi, which is same as SU2 with pi. Is that okay? Okay.
So before Higgsing, is the Higgs branch C2 mod Z2 and then Higgs to a trivial theory?
Yeah, I think so, yeah. Okay, so now once we have this Higgsing, so we can compute the superconductor index out of this SU3. So the idea is that now that we know there's a Higgs branch that gives rise to non-Lagrangian theory, E0 theory, let's start with the Lagrangian theory, which is SU3 with the tensor level 3, and then compute index, and we apply this the Higgs branch algebra. So this is how it's done. So now we have a parameter instanton, and the index is computed this way. This is perturbative part, instanton part, and instanton part again is a 2-part, which is from the north pole and south pole. And after doing this computation, we get the index is written as 1 plus some SU2 characters. So here SU2 two-dimensional is A plus like 1 over A. And then applying this the SU2 character, the three-dimensional representation have 3 terms, and these was the 1/2 factor gives rise to q plus 1 plus 1 over q. So therefore we'll have something like this here, and it is an expansion of this high order axis. Okay. So notice that the symmetry comes from this q parameter, previously of the instanton. Here we have a 3-dimensional representation, and 3-dimensional representation, and 5-dimensional representations, and this. In fact, what is happening is that all other dimensional representation appears. So the even dimensional SU2 characters do not appear in the index. This actually tells you that it is the symmetry of the global the global symmetry is not SU2, but SU2 with the Z, divided by Z2, which is, sorry, it's a flavor symmetry is SU2 divided by Z2, which is SO3.
So why is the Fiaski for what?
Sorry?
Why?
Y is it's like one of the like SO5 omega information associated with omega information. Like X is like with X plus and Y is more like X minus. I'm sorry. X is like epsilon plus and Y is like epsilon minus.
So there is a symmetry between X?
No, I don't think that there is symmetry because there's different quantum numbers.
I mean, okay.
Is there a way to recover the Higgs Branch-Hilbert series from this index?
From the index.
Yeah.
I don't think so because the Higgs symmetry is broken, and you are saying that it will recover, right? So the Coulomb dimension is reduced by 1. So the Higgs branch, the flavor symmetry is broken also. And I'll probably next slide will tell you why it's difficult to reconstruct the SU3 from the local feature. Okay. So let me make sure that this one has SO3 symmetry, unlike the showing the SU2 characters. So this is how actually the Higgsing arises. So Higgsing arises in the shrinking limit of these instanton factors. But as usual, we actually have to be refined how it is actually take place. It is actually take place with together with this epsilon plus shifting. Relating to this is actually q times x squared goes to 1 limit. Is the thing. And as it actually breaks a flavor symmetry, and then we have something called the Goldstone mode as a broken symmetry, and which is like a U1. Their index is take the very simple form. Okay? This is just it refers to the broken symmetry and the Goldstone mode. Okay. And then what we do the Higgsing is that we are going to implement this procedure. So what will happen is that given this SU3 Lagrangian theory superconformal index, and these people told us that after you do the Higgsing, and then they will develop this some residue, which is basically nothing but this Higgs branch limit. And what you do is that you replace this SU3 index with Q. Instead of Q, you replace the Q by 1 over x squared, and you plug in this Q here. The Q appearing here, you replace by 1 over x squared. Okay. And then, because of the fact that after symmetry, the flavor symmetry is broken, there will be the Goldstone mode. We eliminate this.
Does that correspond to the part that you slide it, the brain?
Yes. Sure. So, because of the you actually mix this Q factor here, it's difficult to reconstruct because you don't know whether the X factor. So now you see that all the indexes now is without Q here, right? Reconstructing Q out of this is difficult.
Right, like, so for IE0, indeed the Higgs Branch-Hilbert series will probably be trivial.
Yes, the Higgs branch is trivial.
But in the previous one, for the index of SU33, can recover the Higgs Branch-Hilbert series, which should be C2 mod Z2, just from the index there.
I don't know actually how to construct the Higgs branch of that probably. There should be a way, but I think it's my ignorance and how to reconstruct from the index. Maybe somebody in the audience knows how to reconstruct Higgs branch. Oh, that was your question.
Yeah.
Sorry, I misunderstood that you were asking. And you have a question. Yeah.
One question. So, if one goes to the Higgs branch
Yeah.
of the SU3 theory at level 3, then the statement is that it's an easier theory with a free hypermultiplex, right? Is that the correct statement? And that's the Gaussian mode that you are trying to
Yes,
become.
yeah. Yes, in some sense, yes. Yeah.
Okay.
So pre-hypermultiply is more like you can consider this one as this floating zone brains. You can take it as a pre-hypermultiply, which also have the Gaussian. So this is how it's done. You look at the how actually Higgsing arises, and you plug in this factor, and you also take into account the Gaussian mode, and then it has the index structure. So notice one thing, that unlike this index, it starts from the 1, and the next is the x square, which gives rise to the symmetry of the global symmetry of these. Global symmetry of this is SO3. So if you look at this E0 index, then it does not have the x squared term. This also means that this theory has no global symmetry. So this is also consistent. So this E0 theory has no global symmetry, therefore it should not have x squared. And that is consistent. So the next thing is that how do we make sure that what I compute is right? I mean, you did I did some X branch computation, but there's no reference whether this is right or not, except some consistency that has a global symmetry. So we try something else.
So just to make sure. So you're
Yeah.
saying that x squared term counts certain currents in the theory?
That one has to do with
That's a generic feature of.
yes, it's a generic feature of the index, which is like a current multiplier. It gives rise to the enhanced global symmetry. So as a consistency check, we also did some other Higgs branches, which is also looking at the SU3 with the Sung-Soo level 6. We also realized that there is another Higgs branch going to E0 theory, which is in a similar way you can see. So this is the diagram I showed you before, and these parallel line is associated with the incidental factor. In the shrinking limit, we will have this, and the Higgs actually take places, and we have some free hypermultiply. And this one looks like two copies of the E0 series. So as these 7 brains are connected, one is connected to small triangle, the other one is connected to the bigger triangle. Along the transport direction, 7, 8, 9 direction, this can be splitted, and therefore we will have 2 copies of the E0 theory. So what we did was that in a similar way, we look at the index, we compute the index in a similar way and look at this the structure. And in this case, the Q, the SU2 character appears as not only this odd dimensional, also we have the even dimensional appears. So the global symmetry or flavor symmetry of the SU3 with the Sung-Soo level 6 is not SO3, but indeed is SU2 symmetry. Anyway, we do this fixing, and then our expectation is that the index gives rise to the E0 index square after taking into account the Bose-Stone mode and this pole structure, the proper force structure. We actually compute it, and we have the same result as before. This okay. So we now. What I'm saying is that if you look at the brain well, and we realize that there's X branch give rise to non-Lagrangian theory, then index can be obtained from the original, let's say UV theory, which is Lagrangian. So the IR is non-Lagrangian. Okay. There are yet another one which I mentioned. Which is known as a local P2 with a one-off joint, which has a global symmetry. Also, I mean the idea is similar. So we look at what will be the UV theory along the Lagrangian flow. This one is what we just used, and O-joint comes from the O7 plus, and so we introduce O7, and that corresponds to the SU3 with the Chen-Simon level 1/2 with the symmetric method, which is this. And we do the exactly similar heat sink, but in this case will be slight difference. The flavor symmetry here is the one coming from the instanton of SU3, and the other one comes from the symmetric method. The flavor symmetry is SU2 with SO3. SO3 comes from this instanton, and SU2 coming from the symmetric method. And after doing this heat sink, the flavor symmetry is broken to SU2, and the same Boson mode appears. So we have to take into account this when we compute the index. So the same idea applies. We compute this Lagrangian superconformal index with a particular with the proper assignment of the vigorosities. The Q is the instanton factor, and mu is the mass parameter of the symmetric hypermultiplet. And recombining them to A and B, we get this SU2 with SO times SO3 symmetries. And the pore structure is slightly different, and then after that we get this index for local P2 with one of the joint, which has a x squared term with the SU2 character of 3. So this is indeed SU2. The global symmetry remains after these 6 branches. Okay? But unlike the E0 case of the index, I computed a fair amount of high order, like this x to the 8th order. This kind of heat sink actually is a bit difficult to go high order. If you have some experience of computing superconformal index, going high order or instanton high order is quite challenging. But we don't get to have many terms here. So whenever we apply this kind of heat sink, it will be challenging to go high orders. So it will be good to have some new way of computing. That brings me a second part of my talk. For the given 10 minutes, let me try to go over it very quickly. So a new perspective comes from the idea of using the O7 plus. This work is based on these collaborations. So let me remind you that again, if we have an antisymmetric hypermultiplet or symmetric hypermultiplet, we can construct their branes with the O7 minuses. These are the typical example. SU2 with a 1 antisymmetric is given by O7 minus. Symmetric one has O7 plus. And you can, in a particular Higgs branch of this series, where this middle NS pi brane and the Coulomb branch is aligned, and the mass of the symmetry or antisymmetric hypermultiplet is 0. Then there is some new Higgs branch where this the middle NS pi brane together with their reflected image, you can have the Higgs branch taking them along the transport directions. That actually gives rise to from the SU2 with the 1 symmetry, you get SP, gauge theory. From SU1 with the symmetric method, you get SO theories. And then we found some very interesting relation between the two O7 planes. One is O7 minus and O7 plus. As I mentioned, O7 minus is not much of the problem understanding, but O7 plus is problematic because we don't know how to do it. But having this relation helps to understanding this O7 plus is much better. So we observed a few things. One is that if you look at the monodromy due to the presence of the 7 branes, O7 minus with the 8D7 is actually the same as the single O7 plus. So the monodromy calculation is exactly the same. Also, the brane charges, the O7, the orient chord have the brane charges as a unit of the D7, and they actually also have the same. And therefore there's some, you may think that there might be some relation between these particular combination of the oriented chord with the D7 and with this O7 plus, maybe some relation. So it's in terms of gauge theory, it is a relation between SUN with the one antisymmetry with A flavor. The A flavor comes from the D7s. And is this somehow related to the SUN with the symmetric matter is coming from those? Or as in the previous slide I said there's a O7 minus can be can describe the SP and O7 plus can describe SO. So there might be also relation between SP with A flavor and SO2 and series. So from the grain also, if you draw them in the with the explicit form of the A flavors. So here we will have the A flavor is given like this, and the A flavor of SPM is given like this. Okay. So first notice that the asymptotic the grains look the same. Okay. So what will happen is that is the near the O7 minus. Other than this, other than O7 minus, near the O7 minus, everything looks the same. Okay? So if we have some limit where we can control this mass parameter or tune the masses of the A flavor together with the antisymmetric hypermultiplet, we may be able to connect to the object, the solid for O7 plus. Okay? So this strongly suggests that the brain well strongly suggests that there is some interesting relation between O7 minus with 87 with this O7 plus. So we checked some simple one first. There's something called a prepotential that is capturing the Coulomb branch. It's characterizing the abelian low energy vector theory, which is at most cubic, so it's called cubic prepotential. These are the kinetic term describing this the Coulomb branch metric, and this one has to do with the Chern-Simons level, and this is one new contribution from the vectors and hypermultiplets. And we checked that this cubic prepotential in fact matches exactly if we tune the mass parameter properties. Okay, we call them freezing. So we freezes this mass term associated with the O7 minus that give rise to the same prepotential. And we also look at the Chern-Simons level shift. So usually along this algebraic flow, when we decouple hypermultiplet, the Chern-Simons level shift. For example, this SU3 with a 1/2 Chern-Simons level with a 1 flavor, 1 hypermultiplet in the fundamental representation. Depending on how you decouple with the plus mass or minus mass, you will get like a shift in the 1/2. In fact, this Chern-Simons level shift is described by something called cubic Dickin indices. Cubic Dickin indices given according to their representation. Fundamental is 1, antisymmetric is n-4 for SU and series, and symmetric is n+4. And this one, I mean, you can do a simple arithmetic that you can see that the cubic Dickin index is also the same. The symmetric one is the same as this antisymmetric one plus A flavor. So it seems everything matches. So we go beyond this perturbative level, whether this relation still works. So one of the simplest one is computing Seiberg-Witten curve. Due to the fact that, and thanks to the next speaker, Futoshi, he will talk about this one. So let me skip this part. I'm glad that Futoshi is talking so that I can skip this part. So the option is that Seiberg-Witten also support. So Seiberg-Witten curve obtained with this O7 minus with 87 is turns out to be same as O7 plus with some factor which Futoshi will explain. So and then we can even go beyond the Seiberg-Witten curve. Even partition function, partition function on alpha plus S1 with omega deformation can also see this relation. So one way to compute the partition function, we use ADHM contour integral. These are the terms that appear in the integral of this contour integral. And this is a structure of the SUN with the k-instant terms. So here I omit the Chern-Simons levels. And the fundamental is simple antisymmetric and symmetric shares the some feature in the denominators. And then we can actually check the order by order. Any k-instant order, we found that the one symmetric with 8 fundamental, it turns out to be the integrand is same as just one symmetric. And this is due to this relation that this function can be replaced by this. And the number of this fundamental is exactly 8. Anyway, we can tune this kind of mass parameter with the shifting of the omega deformation the parameter, and partition function level we can exactly see. We can also see that similar relation for SP and SO case. So SP with 8 fundamental is related to the SO. So this kind of the relation occurs. Okay. So let me also skip this. In fact, the reason that I introduced this is because I wanted to use O7 plus to compute this local P2 with a one-off joint, which is a symmetric one. The symmetric is replaced by the one antisymmetric with 8 flavors. So here's the idea. So local P2, the another non-Lagrangian theory can be seen as SU2 with a pi with a one object, and we decouple the one hypermultiplet. Now this is a symmetric, so I replaced this relation with the O7 plus can be equivalent to O7 minus with 8D7 with a particular tuning I call freezing, and I plug in this and I get one antisymmetric with 8 flavors. So SU2 case antisymmetric is singlet, so we don't have to be worried about it. And the 8 flavor minus 1 flavor give rise to 7 flavors. So that means the local P2 with one adjoint can be obtained from the SU2 with the 7 flavor. This SU2 with the 7 flavor, the computation has been done like a long time ago. So the idea is that SU2 with the 7 flavor give rise to local P2 with a particular tuning. Actually, we found that once we do some this freezing, and then we have the index is given, and this index is exactly the same as before, and we can go even higher. So these are the index expression coming from this Hicksing, the Higgs branch. This one is coming from the this freezing, and we have more terms, and the lowest order exactly matches. We get this because of the this is like the theory related by rank 1 to theory rank 1. And computation locally SU2 with the same flavor was done a long time ago, and then we just recycle this theory and freezes this theory to get the easier theory with a one antisymmetric, one Gauss joint. But on the other hand, Hicksing is done with the rank 2 theory, and you do the Hicksing and you lose many terms, and then computing the rank 2 theory index is also demanded. So let me conclude. So in this talk, I presented a way to compute the superconformal index for the non-Lagrangian theory. I introduced the Higgs branch only flow, also introduced this freezing. And for the questions remain that whether we can have a 40 or 60 relation for this relation. And also we are working. We are preparing the papers. We'll deal with 4D and 3D as well. And also it will be interesting to look at the other observable and quantum curve, and also apply Higgs branches numbers. Okay, that's it. Thank you.
Questions?
of the anti-symmetric matter plus fundamental with the symmetric matter, it already appears in the thesis of Shattuck, and it's easier to consider it at the level of full partition function rather than only the instant partition function.
You mean the?
It's just you will get it.
But I think what selection has is a four-dimensional ones with a number of flavors, not
but it's easier to derive this at the level of full partition function as a result of the group theory.
I think we look at the Sedachin's, you mean Sedachin's thesis, right?
Yeah.
I think that their relation, I think if I remember correctly, where was that?
What do you mean full partition function?
If you write it as a full partition function, then
You
you
mean-
just integrate the train character of the matter bundle over the instant moduli space. And for the symmetric tensor, you have E square. E is the universal character of the universal bundle. Then you have E square minus E like square bracket 2, which is the like you. And for the over 2 and symmetric matter you have plus.
Plus, yes.
So the difference is just E square bracket 2. And this is the contribution from fundamental.
I see.
So if you just consider the full partition function, it's easier to see this. If you consider only the instant partition function, you will get out the perturbative part, and the remaining you will not have this simple relation.
I see. Thank you.
Sung-Soo.
Yeah.
I think I asked this to Futoshi, but now I can try to ask you to see if I get a different answer.
Okay.
So, what's the mirror of this? Do you know the mirror of these configurations with orientifolds?
Meaning of this freezing?
What's the mirror? The mirror.
Oh, mirror.
Of these configurations with orientifolds. Since you mentioned, I'm saying it just because you mentioned Cyber-Witten curve. So I wouldn't know what's the meaning of Cyber-Witten curve if we are not talking about mirrors in principle. But I mean, okay, you can talk about Cyber-Witten curve without involving mirrors. But the question
Here,
is,
what?
if
Here
we
we
can
are.
discuss.
We have a perspective that without talking to this mirror. So I think
In my talk, I will say that it's not clear.
in general, orientifolds and mirror is not very clear. So the technique that we are using is this five-ring graph, and we have a dual diagram that captures some characteristic polynomial.
Sure.
Yeah, and then associated with the gauge parameter, we get some curve, the curve, and then we get the this is a interpretation of the M5 configuration, and we take it as the Cyber-Witten curve. But in this way, we don't say much about the mirror of this orientifold.
I see.
I mean, this one has alone, but for example, with the orientifold, it's not very clear, but we can still extend our technique, getting this generalized toric diagram. By the way, this is not a usual generalized toric diagram. The interpretation is just very different, but it is some idea that having the mirror and will be the brain configuration, where then we have to also impose how the O7 minuses apply to the this generalized toric diagram with a particular boundary condition. I assume that Toshi will talk about this. And with this, the basic idea is that this O7 projection relates the point here to here. So there will be some interlocking between the point here and there. And imposing these boundary conditions as well as here, we can still compute the curve without mentioning what is a mirror.
I see.
Maybe Xinwang has opinion. Do you know the mirror of this?
So it's usually a hypersurface, but it's hard to get. I mean, it's big form like this. But
So even with orientifolds, still the mirror is a hypersurface.
I mean, the A model Calabria is usually hypersurface for the when you have it on the. But I don't know the relation with the original.
don't have an oriented fold, it is a hypercircle.
Yeah,
I agree. But with oriented fold,
I think for many cases, like construct the Calabi as a hypersurface.
has a mirror.
Yeah, you can write down here, still a hypersurface.
Are you right?
I mean, I didn't write the paper, but I know it.
Okay. Okay, and then I can thanks.
Any other questions? If not, let's thank the once again. So Panda show up a lot of